Welcome to the lecture 15.1. Today we are going to discuss about the electrocardiogram of the heart, which will help us to understand how the different parts of the heart are functioning. So before we do this, we are going to quickly look through the heart's anatomy. So we are going to figure out the names of the different parts of the heart. And we are going to discuss actually, so what is ECG, so the electrocardiogram, so the ECG is something which tracks the conduction of the electricity from different parts of the heart. So in order to understand the ECG, so we need to understand how actually the electricity is going to be conducted through different parts. So I would like to split the heart into the 4 parts. So we are going to, the upper part of the heart is going to be called as an atrium, and the lower part of the heart is going to be called as the ventricle. And then we are going to split it into the right and left, and we are going to have the right atrium, the left atrium, the right ventricle, and the left ventricle. Again, the heart is going to be split into the 2 parts. The upper part is called the atrium, and the lower part is called ventricle. So please note that here the orientation of the right and left is swapped because we are going to look to the heart anatomy from inside to outside, right? So this part is going to be the left part of the heart, and this is going to be the right part of the heart. So please note that this figure is not for the scale because the left part of the heart is slightly bigger than the right part. So what happens is that, so we are going to say that the heart contracts and then relaxes. So what happens is that you probably have heard the beat of the heart, so it looks like duk duk, then relaxes, right? So it basically, the upper part contracts first of all, then the lower part contracts the second, and then it relaxes. Contracts, relaxes, contracts, relaxes. So we would like to understand what basically happens, what makes the contraction of the heart to happen. Okay, so this is the structure. So we are going to split this into the 4 parts: the right atrium, the left atrium, the right ventricle, and the left ventricle. So the electricity is going to be conducted through the heart using using the cells of the cardiac muscles, which we are going to call as the myocardiocytes. And what does the electrocardiogram is that it traces how actually the electricity is going to be transmitted through those myocardiocytes. If you remember, in the previous lectures, we discussed about the action potential, right? So the action potential, it is increasing and decreasing of the membrane potential, and the signals in neurons or in myocardiocytes are going to be transmitted through this action potential. So at the rest, myocardiocytes are going to be polarized. Essentially, the charge inside is going to be negative and charge outside is going to be positive. And whenever we've got this action potential, it is going to be depolarized, and then it becomes again repolarized, right? So the ECG actually tracks this depolarization of the myocardiocytes. Well, we are going to have the myocardiocytes in different parts of the heart, and the beat, the action potential, is going to be created also in different parts of the heart as well. So the main pacemaker of the heart is called the sinoatrial node, or SA node. Oh, by the way, do you learn, do you have the anatomy already?
Yes, we have body systems.
Okay, you've learned about the heart anatomy already?
Yes.
Okay, then you can help me because I'm not an expert in the anatomy at all. So the main pacemaker or the main beat maker of the heart is called the SA node or the sinoatrial node. So it is going to create the signal, and the signal, the pace, is going to be transmitted to the different parts. So the SA node is located in the top right corner of the right So should I say this top right corner of the right atrium, right? So we call this as the right atrium, and it is located in the top right corner, top right corner. So it is, the signal is going to be transmitted through to the AV node, or it is also called as the atrioventricular node. It is located in the top and bottom left corner of the right atrium. So the AV node is located in the bottom left corner of the right atrium. So please note, so we are going to discuss about this in a moment, that so all of the parts of the heart are able to create the beats, are able to create those action potentials. So we've got this action potential, so it is going to be transmitted through the myocardiocytes from the SA node, which created this, into the AV node. So once the AV node got the signal, it is also going to create another signal, so which is going to be transmitted through so-called AV bundles, or sometimes we call this as a bundle of His. It is going to be located in the middle of the right and left ventricles. So the AV bundle is located in the middle of right and left ventricles. Then the signal is going to be transmitted through the AV bundle. It's going to be split into the two parts, to the right and left bundle branches. So it is going to go into the two parts. So it is going to be split into the two parts. So please note that this, so if you remember the propagation of the action potential, right? Do you remember this? So once the sodium ions to come inside, they're going to open another voltage gated ion gates, so that another ones are going to come in. So the action potential is going to be propagated through that. So then it is going to be transmitted to the Purkinje fibers. Again, so the action potential or the electricity is going to be conducted through all of the parts of the heart and the shoulder. So it is going to be created in the SA node, which is the main pacemaker of the heart. It is going to be transmitted to the AV node, to the AV bundle, or the bundle of His, to the bundle branches, and to the Purkinje fibers. So that every part of the heart is able to create the beat. So the SA node is the main pacemaker. It is going to create the strong beats very, very frequently. So it is able to create 60 to 100 beats per minute. So it is BPM. It's called the beats per minute. So the AV node is also an autonomous beat maker or pacemaker. It is also able to create the beat. So it is going to be created, it is able to create 40 to 60 beats per minute. So its beat is going to be slightly lower or weaker than the beat of the SA node. And usually the beat or the potentials, action potentials, which are coming from the SA node, are going to override the action potential, which is going to be created in the AV node. But you should know that if something happens in between the SA node and AV node, so that the signal is not going to be received by the AV node, the AV node still possible, so it's still able to create those beats. Okay, so the action, so whenever we're talking about the beats, we mean the action potential. The action potential is going to be created in the SA node, right? The membrane potential is going to increase and decrease, and then it's going to be propagated through all of the other parts of the heart. So if something happens so that the signal, the action potential, is not going to be received by the AV node, it is also possible that it is going to create the beat by itself. Then the AV bundles are able to create the beats between 40 to 60 BPM. The left and right bundle branches are able to create to the 20 to the 40, and the Purkinje fibers are also able to create the beats between 20 to the 40 BPMs, beats per minute. So this is how the action potential or the electricity is going to be conducted through all of the parts of the heart. And what we want is we would like to trace this. So we would like to trace how strong it is conducted And by understanding by measuring, by tracing this action potential from the very beginning, from the top right corner until the Purkinje fibers, we've been able to understand the functionality of the heart, and we've been able to even understand where exactly we've got the problems. So, okay. So please note, so we've just said that all of the parts of the heart are able to create their own action potential. So the SA node, which is the main pacemaker, is able to create the action potential, and the shape of the action potential created by the SA node is going to be very much similar what we have seen in the neurons. So please note that in neurons it takes about like 5 milliseconds, where it was like 5 milliseconds, right? So 5 milliseconds, and then in the cardiac muscle cells, in the it's going to be longer. So the shape of the action potential, which is created by the SA node, it's going to be very similar to what we've seen in the neurons. The shape of the action potential, which is created in the AV node, it's also going to be similar to the shape of the action potential created in the SA node. And the bundle of hairs and the bundle of branches, or the Purkinje fibers, the action potential which is created is going to have not just two parts, depolarization and polarization. It's going to have the state of plateau as well. If you remember in the previous lecture, we discussed about this part, right? So when the potential, the membrane potential is going to be increased inside of the cell, and the charge inside is going to be positive and charge outside is going to be negative. So we are going to have the depolarization. And if you remember, there are some other voltage gated ion gates which are going to stabilize the situation. So they stabilize the membrane potential so that the membrane potential is going to stay constantly positive for a while. So we call this state as the plateau. And after some part, the membrane potential is going to decrease again inside, then it becomes negative inside and positive outside. And this state is going to be called as the repolarization. So essentially, these two parts are able to create the action potentials, which are going to have the depolarization and repolarization. And the other parts are able to create the depolarization, plateau, and repolarization. Well, there is a reason why this happens, and we are going to discuss this in a moment. So we are been able to measure the action potential from each of the part of the heart, from the SA node, from the AV node, from bundle of hairs, from bundle of the branches, and Purkinje fibers using the electrocardiogram. So let's discuss about the structure of the electrocardiogram. So the pacemaker and the electric conduction system of the heart is well timed. So it looks like a symphony. It contracts in the beginning on the top part, it contracts. Then after some time, it contracts in the lower part. Then all of the cells in the heart becomes depolarized. And after a while, it's going to relaxes. So the contracts, relaxes, and then relaxes. Okay, so let's look to the ECG. Are you here? I hope that I'm not talking with myself, right? No? Okay. So let's discuss what is the electrocardiogram. So it consists of the three words: the electra, which is the conduction of the electricity; cardio, it's the conduction of the electricity in the heart; and the gram, which is the graphic, right? It's electrocardiogram, as it states in its name, is the visualizing the electric conduction of the heart. The electric conduction of the heart, visualizing the electric conduction of the heart. So you probably have seen this kind of graph before. So have you ever tried to, do you know nowadays there are some like smart watches or so, you can measure your ACG using them as well. But usually if you go to the hospital, the ACG is going to be taken by putting the leads. So they are going to put positive and negative charge into the different parts. So there are actually six of them. So they're going to be put into the right arm, into the left arm, and into the left leg. And then we are going to measure the conduction of the electricity through the heart. So, and we are going to get this kind of graph. So what we would like to understand is, so we would like to understand every part of this graph. What is this part, and why we've got this kind of curve? What is this part? What is this part? What is this part of this graph? And what is this part, and this part? So all of these parts is important, and it appears. So once the action potential is going to be transmitted through the different parts of the herd, we are going to track this, and we are going to visualize this into this kind of graphs. And the length here basically means the time. Okay, so by understanding the timing, so how long it takes, so there are like norms, how long it should take for you that the signal is going to be transmitted from the different parts of the herd. So you can even measure this. So for example, if the length is different, then you understand that that particular part of the herd is not functioning well. So one more time, this is the full structure of the herd through which the electricity is going to be conducted. It is going to be created in the SA node. It's going to be conducted to the AV node. Then through the AV node, it's going to be goes through the AV bundle. Then it's going to be split into the two parts, and it goes through the left and right bundle branches. And at the end, it finishes up in the Purkinje fiber. So this action potential is going to be transmitted through all of these parts. And once all of the cells are going to be depolarized, it's repolarizes again. So it relaxes. So the state when all of the cells of the heart, all of the myocardiocytes are depolarized, it's like contracts, it's the state when it contracts all of the parts. Then after sometimes it relaxes, so it repolarizes again. So the ECG actually traces how depolarization wave moves at each heartbeat. So if you remember, so if you don't remember what is called the depolarization, let's look to this in more details again. So I would like to look to one of the cells, one of the myocardiocytes of the heart. If you remember, we discussed about this in previous lectures. So we've got the plasma membrane or the membrane potential, which is going to separate the charge. And we are going to have negative charge inside and positive charge outside. And at the rest, when all of these processes are going on, so for example, the potassium ions are going outside, sodium ions are coming inside through the special gates, the charge inside is negative and charge outside is positive, and it's equal to the minus 90 millivolts for the myocardiocytes at the rest, and at the rest it is polarized. But once there some signal is coming in, the sodium ions to come inside, and it changes the charge inside, it becomes positive inside and negative outside, positive inside and negative outside. This state is going to be called as the depolarization. Depolarization. And all of the cells of the heart are going to be depolarized, and ECG is going to trace how this depolarized. All of the cells are depolarized. So this is what we call as depolarization and depolarization. And after some times, it becomes again repolarized. So we've discussed about the reasons why it happens in more details in previous lectures. It becomes like changing the concentration of the different ions inside and outside these cells, right? So at the rest, you've got positive outside and negative inside. At the depolarization state, we've got positive inside and negative outside. So now I would like to put the two, one lead, and I would like to put the two charges, so plus charge and negative charge. So I'm going to send the electricity. So I'm just going to put the two things here. So one is going to be positive charge and negative charge. I'm going to give the positive and negative charge to here. And this invisible line, which is going to connect these two positive and negative charges is going to be called as the lead. So we are going to connect the positive and negative charges using so-called lead. Okay, so I'm going to put the positive charge to here, to my right arm, and negative charge to my left leg. And then I'm just going to measure the so-called dipole. So what is a dipole is essentially, it's something, it's a vector which measures the charge difference inside the herd, or through the sequence of the myocardiocytes. So if you remember, we've got this state at the rest when everything is positive outside and negative inside. But once the signal is coming, the action potential is going to be propagated through the cells. It is becoming positive inside and negative outside. But let's hold on the state when the signal is transmitted until the half of the cells, okay? So until half of the cells here, so it is transmitted here, so it becomes positive inside and negative outside, but it is not transmitted to the rest until the end yet. So at this stage, we are going to measure the charge difference inside the cell. So you can see here that you've got this charge difference, positive and negative inside the cell, right? It is transmitted through the cells, and this charge difference is measured so-called dipole. It's the vector which moves from the positive to the negative. So, or you can understand this, it moves to the positive outside. So if you remember, we discussed about the electric gradient as well. So it is similar thing. So when the electric gradient is moving from positive to the negative, usually. This is the same for the dipole. So the dipole is going to measure the charge difference. So it usually goes through the lead, which connects the positive charge and negative charge, which we put outside. And it is going to move through that lead. So what we want is, it appears, so those leads which are connected to you are going to be able to trace this dipole. The higher the difference of the charge, higher the graph of this dipole which you are going to get. So the dipole is the vector. It moves to the positive outside. Okay, and the length or the magnitude of this vector is proportional to the difference of the charge inside the cell. So the higher the difference, bigger the vector, or the longer the vector. The lower the difference, the shorter the vector is. Okay, again, you put the positive and negative. The dipole is moving, so it always moves to the positive outside. It doesn't move always to the plus outside, right? So you can see here that in this example, the dipole is moving in that direction, which is positive here, right? So it moves always when you've got positive outside the cell. Or you can understand this as it moves from positive inside to the negative inside. Okay? So the length of the dipole, which is called the magnitude of the dipole, defines the charge difference. Okay, so now let's look to this graph. So it appears we can measure, we can trace this dipole using this kind of graph. So at the rest, when all of the cells are going to have negative charge inside and positive charge outside, you're not going to have any dipole because there is no charge difference at all. So any charge difference at all, so you're not going to have anything, so you're simply going to have the horizontal line. But once the charge is transmitted through, so you've got the situation when some part of the herd or some part of the cells are depolarized and the rest are still polarized, so there is a dipole is going to be created, and you can measure this dipole. So and how we are going to measure is we are going to look to the direction of the dipole. And if the dipole is moving to the direction of the plus charge, which is outside the herd, then we are going to have the curve which is going to look upward. So we are going to draw this like this. Okay, So it's going to have the curve, which is going to be positive. So if you look to this charge as the y-axis, and if this part is going to be the x-axis, and if you remember, this part is y is equal to 0, right? And if you have no dipole inside the cells, so you've got all of the cells which are polarized, then simply you're going to have horizontal line. But if there is a dipole is created, depending on to which direction this dipole looks like, so looks to the positive or to the negative, you're going to have this curve either above the x-axis, either below the x-axis. So again, so we are looking to the situation when you've got all of the cells which are polarized, then it starts like it looks like, so if you stay all together, so a couple of students together, and if you start making the waves, right? So you start, so at the rest, when you're not moving, so you've got this no dipole. But now, so one hand of you is up, right? It's about to transmit the signal to your next hand, but it didn't. At this stage, there is difference in charge. So this part is positive, this part is negative. So, and this is going to be measured using the dipole, okay? But now when it's going to be transmitted to all of the parts again, so you've got depolarized cells, and is there any dipole there inside the cell? No, because the dipole again measures the charge difference inside the cell. When all of the cells or all of the parts are depolarized, it means that all of them are going to have positive inside and negative outside. You've got again no dipole. And what you are going to see in the electrocardiogram is again the horizontal line. But again, if you remember, the heart contracts from the upper part to the lower part, and then it relaxes. Contracts, then relaxes, right? Relaxes means that all of the cells are going to repolarize again. So it means that it becomes negative inside and positive outside. And again, it happens from the left to the right, okay? So at some point, so the cells are going to start repolarizing. So let me draw this again. So one more time. So you've got the cells here, so which are negative inside and positive outside. So once this cell on the left is going to get the signal, it start depolarize, and it's going to transmit the signal to the right. So that, and it becomes like this. So it's plus here, minus, plus, minus, plus. At this stage, so the signal is created here, for example, then it's transmitted to there. So at this stage, we are going to measure the dipole. So the dipole moves into this direction. Why? Because you've got positive charge outside, okay? But after some times, all of the cells are going to be depolarized. But once all of the cells are depolarized, then they start repolarization again, right? And it starts from the left part. You've got now here the minus inside, plus outside, minus inside, plus outside, but the others are still depolarized. So it's going to be plus, minus, plus, minus. So do you see the difference between these two graphs? So in the upper part, so the cells, the signal is transmitted, right, from the left to the right. The action potential is going to be transmitted from the left to the right, and the cells are going to start depolarizing one by one. And once all of the cells are going to be depolarized, the cells are starting repolarization. So it starts again from the left to the right. So the repolarization means that they become again negative inside and positive outside. So is there is dipole now at this stage into this graph, in this graph? Is there is dipole vector?
Yes.
Yes, and it moves in which direction? Do you remember? It moves in the direction of the positive outside. Now it moves in this direction, right? Because you've got positive outside, okay? So it moves in this direction, and what you are going to have on the graph is, so do you understand this? I'm just showing this in this graph. So you've got positive here, So positive, positive, negative, negative. Because those cells on the left start repolarization, and they are going to start repolarization one by one. The one in the left, it's going to be repolarized, then again repolarized. So, but the others on the right still polarized. And at this stage, I'm going to measure the dipole, okay? And the dipole vector now moves into that direction, again, into the direction where we've got positive charge outside. And if you now look to the direction of the dipole vector, you can see here that the dipole vector moves to the negative here, right? So to the negative charge, which we put outside. Whenever the dipole is moving into that direction, what you're going to trace, what you're going to have in the graph is the curve which is below the x-axis. If you remember, whenever the dipole is their dipole, you've got the non-zero, non-horizontal curve, and depending on whether the dipole is moving to the plus or minus, you're going to have this curve above the x curve or below the x curve. Whenever there is no dipole, you're going to simply have the horizontal line again. Okay, so this is how we are going to measure the dipole. This is how we are going to measure the, we are going to trace the depolarization of all of the cells. Well, everything is not so easy as it might seem to you at the first glance, because there are vectors are playing a role a little bit. So if you remember, we've learned about the vectors a little bit, right? So now, when you've got this lead, do you understand what is a lead? So the lead is something, so the electromagnetic field, which is going to connect these two charges, the positive and negative one. And whenever this lead is horizontal, or it lies into this sequence of the cells, then you can measure this dipole more or less easily. So you can draw this dipole, and so depending on whether the dipole is moving to the plus or moving to the minus, you're going to draw this curve. And the height of this curve again is going to depend on the length of the dipole. Higher the charge, higher the higher the curve. But the thing is, so sometimes you're not going to be able to trace this dipole because your lead is going to be in the different direction. For example, you put this lead. So if you go to the ECG, so you might have these two leads, and so put into your right and left hands or arms. And this lead is going to be connected like this, but your electric conduction of the heart is moving in the diagonally. Okay, again, you've got this heart. So the electric conduction moves diagonally, but you put these two leads, or the lead into your right and left arm, so the plus and negative here, and the lead is going to be connected like this. The electric conduction is moving diagonally. Okay, so again, so you've got at the rest, you've got all of the cells polarized, and they start repolarization or depolarization, sorry. So from the left to the right. So those cells here are depolarized. If you remember, the depolarization means that they become positive inside and negative outside. And they
I have a question.
Yes.
What is lead? Is it an element? It's completely different.
Excuse me?
What is lead? Is it an element?
Oh, lead, it's electromagnetic field, which is created by these two charges. So you put these two things, and you're going to connect them into the electricity, and it is going to create the electromagnetic field, so which we call as a lead. It is not visible, so it's going to be invisible. So you're going to see this in the next picture. Okay.
And another question is dipole controls the direction as well?
Is that one controls the direction of what?
The dipole moment controls the direction as well. For example, to the right, to the left, where it goes.
No, it's not going to control the direction. The action potential is moving, and the dipole moment is going to be created as it moves through the cells. So you've got a lot of cells there, right? So the action potential, which is going to be created in one of the cells, should propagate this through the cells. And you've got this moment when you've got this couple of cells in the beginning which are depolarized, and the signal is still transmitting. It's not at the end, and the others are already, so it's depolarized plus inside, and the others are polarized still. So at this stage, when you've got a couple of cells which are depolarized and the others are polarized, there is a dipole because there is a charge difference here. Okay, so the dipole doesn't really, okay, so the direction of the dipole is going to be always moves from the positive to the negative. Okay, so if you look to the inside, so it's going to move from positive to the negative into that direction. And again, is if you're going to put your lead exactly in that direction, if you're going to put your lead to the plus here and minus here, then you're going to be able to measure this dipole. The dipole is going to be created and does it, so it has a different direction, but the direction depends on your orientation as well, right? So how you're going to put your lead, how you're going to orientate your lead. So you're going to orientate your lead differently as well. So our goal is to track this dipole. The dipole is going to be the electric difference. Okay, so we just would like to track this. Okay, so whenever you've put this lead horizontally like this now, and the electric conduction of the herd is moving diagonally, how we can track this dipole now in this stage. If you remember, you've got this lead between this two minus and plus. So you've got this line, horizontal line. And how we can measure this vector, which is not in that line anymore. Previously, you've got this vector, which was in that line, in the horizontal line. Either it moves to the plus, and you're going to have this curve, which is about the x curve. Either it moves to the minus, and then you're going to have this curve, which is below the axis. So now you've got this vector, which is not on this line. So what we're going to do is we are going to find the projection of this vector onto this horizontal line. Okay, so let's find this. So the projection of this vector onto this horizontal line is going to be this vector. Okay, well, do you see that this vector, which is on the projection of the on the lead of this dipole vector on the lead, is shorter? The magnitude of this vector, which is on the lead, is shorter. So that is why, if previously you trace the dipole with the higher graph, in this stage you're going to trace the dipole with the lower graph. Do you see this difference? So previously you've got this graph a little bit higher because the dipole was exactly in the direction of your lead. Okay, now it happens that if you've seen the anatomy of the herd, we've seen that the signal is going to be transmitted through the different parts, and they have a different geometry, different orientation, right? And your lead direction is always the same. So you put this T plus and minus, and the lead direction is always the same. And depending on how they're moving, you're going to have these graphs, either upper, either lower. And it is really important for us to understand how to trace those dipole. Okay, so we're going to make the projection. But what happens is that the electricity is going to be conducted through the cells. So the action potential is going to be conducted through the cells in that direction. So in this direction now, you've got this dipole, which is moving to the positive outside, right? And your lead now is completely perpendicular to this vector. So if you remember, the idea would be if the direction of the vector doesn't match with the direction of the lead, what we are going to do is we are going to find its projection onto the lead. Well, what is going to be the projection of this vector, which is completely perpendicular to this lead, is going to be simply the point where there is no vector projection of this vector onto the lead. So what you're going to measure is, you're not going to be measuring anything. So you're going to have, again, the horizontal line, even though there is a dipole. Again, so the electricity is going to be conducted through the herd differently, right? So what we want is, we would like to trace this. We want to measure this. The thing is, if we are lucky enough and the dipole moment is going to be on our lead, we are able to measure this. Or it's going to be a little bit different from our lead, so we can measure its projection onto this lead. The problem becomes if the dipole is completely perpendicular to the direction, to the lead, then we're not able to measure this. So we might think that there is no dipole at all, because if you remember, when you have no dipole, you've got the horizontal line. But it appears having the horizontal line on the graph doesn't mean that you don't have the dipole. It means also that you're going to have the perpendicular dipole to your lead. So this is the reason why we are going to have leads in the different directions, not just one lead. So we're going to measure the electric conduction of the herd, just not just with one lead. We're going to measure this with 3 leads. So we are going to we are going to have the 3 leads put to the left left arm, to the right arm, and to the left leg. And so if you if you go to the ECG, you're going to have the three lines of the readings. So this is the lines of the readings taken from each of the lead. Okay, and again, you're going to have the lead, which is like negative to the positive. So the direction is going to be like this. And as the action potential starts, it's going to be created in the SA node, and it's going to be moving through the SA node to the AV node and through other parts of the herd. So the different leads are going to measure, are going to trace this dipole moment differently. Okay, so this is what we call as a lead. So lead is not something which you're going to put onto your body. So you're going to put the plus minus charge, plus charge into your, so into your left, you're going to put minus minus. Onto your right, you're going to put plus plus, and onto your left leg, you're going to put plus minus. And those charges are going to create the electromagnetic fields. And whenever you've got this dipole, they're able to trace those dipole. Okay, so now let's discuss how this dipole is going to be traced once the signal is going to be transmitted through all of the parts of the herd. So whenever the signal is created in the SA node, and it's going to move in the direction of the AV node. Okay, so there are lots of cells there, but mean vector, the average vector, is going to move in that direction. It's going to be moving from the SA node to the AV node. Okay, so you've got all of the cells here, so and the rest, they've got minus inside and plus outside. But once the action potential is created, they are going to start depolarizing. It's going to be plus inside and negative outside. And if you look now to the direction of this depolarization and to the direction of the lead, so they are in the same direction, right? And this dipole now is in the direction of the plus. So that is why, what kind of graph we are going to have on the ECG, on the electrocardiogram? What kind of graph? We're going to have horizontal, or the graph which is above or below?
Above.
Above, right? So we are going to have this kind of graph. So this curve is called the P wave. The P wave is responsible to trace the dipole moment between SA node and AV node. If you don't have the P wave, if its timing is longer or shorter, or if you don't have this, if you have this weaker or higher, you can understand that there is problem between AV node and SA node. Okay, so whenever the electricity is going to be conducted from SA node to the AV node, we're going to be able to measure this dipole using this P wave. Well, it appears whenever the action potential is transmitted to the AV node, it is not going to be transmitted further right immediately. So there is some time delay. So the AV node keeps the signal for a while. So if you have seen some animations of the herd, you might see this also, like it contracts at the right, at the upper part. Then after sometimes it contracts in the lower part and then relaxes. It's like duk, duk, and then relaxes, right? So there is some delay between the contraction of the upper part and the lower part of the herd. And this contraction happens because the AV node keeps the signal for a while. And the timing of this interval is going to be also traced using the by measuring the dipole moment. There is no actually dipole moment there, but we can still measure this delay, and this delay is going to be called as the PR interval. So now, once the signal here is transmitted from the AV node to the AV bundle or bundle of His, so it's going to be moving like this, right? And what we are going to have, oops, sorry. How to go back? Oh, it's okay. So it appears once the signal is going to moving through the bundle branches, the direction of the depolarization, it appears, is not going to be in the direction of the bundle branches. Its direction is going to be in the direction of the right part of the herd. And the reason is because the left part of the herd, this red part of the herd, is bigger than the right part. So the signal goes to there first of all, then it's going to be transmitted, like it's go downs, but slightly in that direction as well. So the mean vector now is going to look like this vector. And if you draw the mean vector, so if you remember, if you've got this dipole vector in a different direction than your lead, so the way how you're going to measure is to find its projection into the lead. So obviously the projection of the dipole into the lead is going to be something like this vector, right? So you see, so this vector now moves in which direction? To the plus or to the minus? So this is going to be the projection of the dipole into the lead. So it moves to the negative direction. So that is why you are going to trace this as the graph, as a curve, which moves, which is below the x curve. So this is what you're going to have here. And this is going to be called as the Q wave. And the Q wave, again, is responsible to the transmission of the signal from the AV bundle through the bundle branches here, okay, in the beginning. So you're going to have this Q wave. But now, once the signal is here, so you've got all of this depolarization direction, so moving towards to the plus, to plus here. And if you look to the mean vector, so mean vector is, I'm just going to add all of these vectors geometrically. Do you remember we've learned about the addition of the vectors geometrically? If you've got, for example, this vector and this vector, you can add them geometrically, and this is going to be called the mean vector. Okay, and the mean vector now is going to be the dipole vector. It is moving again in the direction of the plus, right? The mean vector is going to be moving in that direction of the plus. So that is why we are going to have this R wave. So the R wave now is responsible to transmission of the signal through the bundle branches at the bottom part of the bundle branches. So the signal now is going to move in the direction of the Purkinje fibers, right? And you may see here that the signals are moving, moving in the direction of the Purkinje fibers. And if you look to the dipole moments there, and if you look to the mean vector of the dipole, you're going to see here that it's moving to in the direction of the minus. So this is the reason why you're going to trace this as the curve which moves, or which is negative, which is below the x-axis, and this is what you're going to see here. So the ST interval is responsible to something which is called the plateau, or now all of the vectors are depolarized in the herd. So it started depolarization from the SA node. So the cells were depolarizing here, then the signal was moving, and it starts depolarizing all of these cells here. And once all of the cells are depolarized, before it repolarizes, it appears, it creates a small signal as well. And this signal is going to be called as a T wave. So the ST interval is something which is responsible to the state of plateau. If you remember, the action potential especially in the AV bundle, AV bundle. So this is the AV bundle, and the AV bundle and the bundle branches and the Purkinje fibers, they have this plateau state as well, right? So they are depolarized, but they're not going to be immediately repolarized. So they're going to stay for a while, and the state when the membrane potential is going to be positive. And this ST interval is going to trace this moment. So this timing when the action potential is going to be in the state of plateau. But once all of the cells are going to be repolarized again, so this is going to be traced using the T wave. So now all of the cells again are repolarized. They're negative inside and positive outside. So I know that it might be a little bit complicated. So let's go through all of the processes one more time. Again, the P wave is responsible to trace the dipole when the electricity is going to be conducted from the SA node to the AV node. Then whenever the signal is going to be held on in the AV node, we can measure this delay using the PR interval. So then whenever it moves through the bundle of His, so the AV bundles, we can trace this using the Q wave. Whenever it is in the bottom part of the bundle branches, we can measure this with the R wave. Whenever the signal is moving towards the Purkinje fibers, we can measure this still using this R wave in the upper part of the R wave. And whenever all of the cells are in the state of the plateau, we can measure this with the ST interval. And whenever all of the cells are becoming repolarized, we can measure this using the T wave again. So this is simple, the review of how the electricity is going to be transmitted through the different parts of the herd. So we can trace this using the different curves. We actually are measuring the dipole. And by just understanding the shape, of each of the part of this ECG, we can understand where the malfunctioning, so the position of the malfunctioning parts of the herd.